Good morning, ladies and gentlemen. I'm sorry we can't get to the conference site. Here, please allow me to explain the main ideas of our paper via this video. Our paper named A Toolkit for Analyzing Concept Evolution in Computing Curricula, and the authors come from UCAS. We investigated the ACM computing curricula from 1991 to 2030 and found that the number of concepts are increased by 5 times. In this paper, we developed a solution to explore the body of knowledge of computing. The proposed toolkit uses a graph model to represent the disciplinary knowledge structure. Our study not only intends for computing discipline, but also tries to develop a general framework and toolkit for analyzing other disciplines' curricula. The holistic solution should overcome problems across all areas as the fourth line shown, and the fourth column shows existed software tools for information extraction, storage, and virtualization. This table concludes the analysis for available tools, pros and cons. Each of those tools provides part of the feature we need, but no single one meets 4 requirements. That is the reason why we decided to make a tool to solve the problem. The ACM computing curricula is one of the most impactful course guidelines for undergraduate study programs in computing field. This paper only discusses computer science of the computing curricula. In 1968, ACM released the first volumes of computing curricula. A decade later, Curriculum 78 was published, and since 1991, when ACM and IEEE Computer Society began working together on computing curricula, 4 volumes are released. They are CC 1991, CC 2001, CS 2008, and CS 20. Why do we exclude the site Curriculum 68 and 78? The reason is that those disciplinary knowledge are organized in the form of exemplary course, which is significantly different from the later 4 volumes in terms of knowledge structure. The table shows their statistic output. The figure shows the overall architecture of TSCE, which integrates several technologies to provide a qualitative analysis of concept evolution. The figure starts on the left with raw computing curricular data such as PDF files. The body of knowledge is extracted from them and saved in XML format. Concepts annotation is subsequently employed to identify disciplinary concepts. The knowledge structure representation stage explains how we extract the annotations and build a graph model of the knowledge structure for later analysis. The graph analysis stage shows the approach we performed on the graph model. Finally, the results information is exported as CSV files and presented in different kinds of diagrams, as described in the reporting and virtualization stage. First, we must extract the body of knowledge and save them in a unified structure so that they can be processed by the component for concept annotation. The body of knowledge section is to be picked out from the whole curricular report manually. A parser implemented by Java is responsible for parsing the section to extract keys, cues, and topics. We only present some results of concept vitality in this paper. As we can see, the increasing number of concepts clearly indicates the expansion of the CS discipline. From the perspective of concept vitality, we may find most concepts of CC 1991 become obsolete, while in CC 2001 and CS 2008, obsolete concepts only takes a small part. In CS 2030, the large number of new concepts contributes to the large portion of reliable. We may find the most topics in the SOS, IM, and AL are always considered important for undergraduate curriculums, which is in accordance with their fundamentality in CS. Specifically, we thoroughly observed at the concept vitality of architecture and organization from CC 1991 to CS 2030 in red fig. The count of concepts keep increasing in first 3 volumes but shrink at CS 2030. The large proportion of obsolete concepts in CS 2008 contributes to the decrease. In order to deeply understand the change of knowledge area in each curricular volumes, we draw the reader chart based on the distribution of concepts number in the knowledge area. We have observed that the content of knowledge area has been increasing year by year. Some areas always have an important role. The change of human knowledge is like the evolution of this figure. Although the importance of each field is fluctuating, in the overall trend, people's knowledge area is improving constantly. In this figure, the 4 vertical columns block represent the topic of different curricula. The height of each block stands for the weight of this topic in its curricula. The lines between different vertical columns represent the mapping of topics into curricula. Thicker the line is, more parts of the topic in the left columns transfer into the topic in the right column. In this paper, we present TACE, a novel toolkit that enables people to explore the concept families development of computer science thoroughly. In future, we hope the method can be applied to other subjects.